Previously, we used a transistor amplifier to illustrate how feedback can be used to remove certain kinds of distortion, noise, hum, things of that sort. What I'm going to be doing in this video is a little more general overview of feedback, but as a little bit of introduction to that, what I have on the screen is the analog discovery displaying the input and output of a Class AB transistor stage. I'll show you the circuit in a minute, but you'll probably remember it from the Class AB amplifier videos. The yellow trace is the input over here, and the blue trace is the output. But I have the channels adjusted so that there is a roughly 11 or 10 to 1 difference between the input and output. So I have the input set 10 times more sensitive than the output, so that they essentially look like the same wave. In other words, when the two are identical, that means that the overall stage gain is 10 or 20 dB. On the left is an XY display of these same two waveforms. And you see that the XY is relatively linear. Now, don't pay too much attention to the fact that the two waveforms aren't right on top of one another. That has to do with the fact that when it traces in one direction, it is slightly offset from when it traces in the other. In other words, it's more of an artifact of what we're doing here. What I want to do now, however, is short out one of the diodes in the AB output stage. You notice that there is severe crossover distortion shown here. But notice that because I'm shorting out the positive diode, that is, there are two diodes in this, one that biases the negative stage, in other words, the stage that conducts when the input is negative, and the other which conducts when the input is positive. I'm shorting out the positive diode for now, and you see that we get a fair amount of crossover distortion. And it's rather obvious in this diagram what that looks like. Now what I'm going to do is I'm going to change the feedback from local feedback to global feedback. And let me point out that with global feedback, you notice that the amount of remaining distortion is relatively small. And while there still is distortion in the amplifier, a large part of the distortion is being removed by the negative feedback. Now, if we had more loop gain in this circuit, we could get even more of a reduction in distortion. But this is only to illustrate. Let me now go back to local feedback again and global feedback. So now let's take a look at that on the schematic. Here is the circuit that we're working with, and as you recall, the diodes in the output stage are inserted to convert this from a Class B amplifier into a Class AB amplifier. That is, to produce enough voltage difference to offset the VBE, that is the base to emitter voltage of each of these transistors. By doing that, these transistors are very close to conduction, even with no signal applied. So it takes much less signal to produce an output. That reduces the crossover distortion. What I have been doing is shorting out one of these diodes and then changing the feedback from local, that is, from the output of the op-amp to its inverting input through a resistor divider, to global feedback. That is, instead of deriving the output signal or the feedback signal from this op-amp, we're deriving it from the output of the amplifier. So that is providing global feedback. In other words, feedback around the entire circuit. As a result, the global feedback compensates for a large part of the distortion present when I short out this diode. Now, we also showed earlier that this kind of global feedback can also reduce other kinds of distortion so long as it occurs within the loop. That is, hum, noise, and other things in addition to crossover distortion. What I would like to do now is a little bit more general discussion of feedback, particularly of the effect of global feedback and how it can be derived, that is, where you can obtain the signal for the feedback, and how you combine the feedback signal with the inputs. What I've shown here is what might be called the classical signal flow in a feedback system. And what I'm going to do next is show how this equation, that is the equation where the overall gain of the system can be determined by knowing the gain of the forward element, I call that little a, and the gain, or I should say actually transfer functions, but call it gain for these purposes, of the feedback. And if you have seen this before and know the derivation and so on, you might want to skip forward, but two of the reasons that I'm doing this. One is I've gotten some favorable comments from people who prefer that we do these simple explanations, but in enough detail that they can actually understand the steps. Also, I recall when I took control theory the first time, I actually dropped the course because I found it so mathematical, and I was taking a heavy course load already. So I wound up dropping the course because the mathematics were just overwhelming. Now, I admit it was a bit more than this. It was differential equations and matrices and eigenvalues and all of that. But nonetheless, the mathematics can be overwhelming. So what I'm going to try to do is to show you how we derive this equation for the system gain. This voltage is simply the input voltage, V1, minus the feedback voltage at the output of the feedback network, V4. V3 is simply V2 multiplied by A. V4 is simply V3 multiplied by F. So here's how we derive that equation. First, we write that the A, that is the closed loop gain of the system, is the output voltage, V3, divided by the input voltage, V1. That is V3 divided by V1. Now we notice that V3 is just A times V2. Notice V3 is A times V2. So we can write this divided by V1. We know that V2 is simply V1 minus V4. This is V2. This is V1 minus V4. Therefore, we can write this as A times V1 minus A times V4, which is F V3. Now we're going to copy this back down over here, the only difference being that I'm going to move the V1 over here beside A. So we have V1A equals A V1 minus little a F V3. So V1 times A equals A V1 minus, I should say little a V1 minus little a F, and then we replace V3 with capital A V1. Now, I divide through by V1. That gets rid of this V1, and this V1, and we get A equals little a minus little f, capital A. Now I move this part over to this side, and of course it becomes a plus. So it's capital A plus little f, capital A equals little a. Now I factor the A out in front. It becomes capital A times 1 plus little f equals little a. And now I think you can see that we get, by taking this A and dividing by 1 plus AF, we get capital A equals little a divided by 1 plus AF. And of course that is the result that we got there. Returning briefly to the circuit in which we've been demonstrating the difference between global feedback and local feedback, notice that we're taking the feedback from this point and feeding it, when we have the switch in this position, through this resistor to the negative or inverting input of the op-amp. So what is the feedback network? Well, it's this resistor and this resistor to a virtual ground. In other words, it's a voltage divider. It's a simple resistive voltage divider. So in this case, what we are doing is sensing the voltage at this point. And this is what is known as node feedback or node sampling. There are essentially two ways to sense the output. One is node sampling, which senses a voltage. The other is loop sampling, which we'll talk about in a minute, which senses current. The way you have to do that is you actually have to sense the current in this lead. And to do that, of course, you have to open the lead, insert something like a resistor in it, measure the voltage across that resistor. And we'll talk about that in a minute. But this is node sampling. The second thing is there are two different ways of doing comparison. In this case, we're using an op-amp, which simply subtracts this voltage from the input voltage. Another way to do it would be to insert something in series with the input signal. In other words, in this loop here. And that would be called loop comparison. This is node comparison. We're comparing this node to this node. So let's look at the four kinds. Here is loop comparison and loop sampling. Notice that we are sampling the output current. The output current has to flow through the feedback network. That is loop sampling. Furthermore, the output of the feedback network is in series with the input, or in the input loop. That is, the input signal has to go through the feedback network. That is loop comparison. We can use node sampling, that is the voltage across this circuit, and loop comparison. Or we can use node sampling and node comparison. That is, we sample across the output, the voltage, and we apply our feedback signal across the input so that the signal generated by the generator and the signal generated by the feedback loop add to each other. Finally, there is node comparison and loop sampling. That is, we're applying the signal across the input, node to node, but we are sampling the output current. Coming back to this system, we are using node sampling because we are sampling the voltage off the output node. In other words, the voltage between this point and ground. We are then feeding that back, and we are using node comparison because we are using the inverting node of this amplifier for the feedback signal, and we are applying the input signal to the non-inverting input. Class A amplifiers, you may recall, we used this simple 3904 circuit, that is a NPN transistor 2N3904. But if you remember, we left this resistor unbypassed. In other words, we did not put a capacitor across it. And we talked at the time about the fact that by leaving this unbypassed, we were essentially giving this feedback. Well, this resistor is in the input circuit, so any voltage developed across this that's fed back from the output is going to be in the input loop, so it's loop comparison. Furthermore, all of the output current flows through this resistor as well, and therefore it is loop sampling. In this circuit, this is a 3-transistor amplifier. These are the load resistors for each stage. This is the input. The output is developed across this load resistor, very much like the circuit we just saw. However, notice that in this case, there's no emitter resistors. There is, however, a resistor from the output back to the input. So what is this? Well, it is node sampling, because we are sampling the output across this output stage. We are feeding it back, and we are feeding it back across the input, so it is node comparison. So I hope this helps a little bit, particularly in relating some of the more esoteric elements of feedback theory. Look forward to some more videos, but probably on the subject of feedback. I'm going to make this the last in that series. So in the meantime, have a nice day.